This paper reports on the experience gained with digital craftsmanship to realize a didactical model of herringbone masonry in a circular dome. The comparison with an already existing wood model gives the clue for some considerations on the value added to the production by the 3D printing process. This paper is authored by Alexia, Charalambous, Giuliana di Iacovo, Federica, Loccarini and me from the Department of Civil and Environmental Engineering of the University of Florence. To understand the aim of the model, it is necessary to step back to the 70s. During the Congress held on the occasion of the 400th anniversary of the birth of Filippo Brunelleschi, Mason and Di Pasquale presented their interpretation of the static of Brunelleschi's dome and substantially agreed in the interpretation that would have been recognized since then. The dome, although built on an octagonal plan, is in fact a circular one. In agreement with the detailed description reported by Manetti and successively transcribed by the main researchers, the internal profile of the rib is described by a circle, which center corresponds to 1/5 of the internal diameter. The external profile is described by a circle having the same center that, in this case, corresponds to 1/4 of the external diameter. Two adjacent ribs are connected by a portion of a barrel bolt shaped according to an elliptical cylinder that forms one of the 8 segments. The octagonal plan of the dome makes recall a cloister vault, obtained by crossing of 4 ogival barrel bolts with incident axis according to an angle of 45 degrees. Indeed, the bricks are placed on surfaces of cones, as if the building had a circular plan. The dome is, actually, a circular one. This makes the structure stronger and, moreover, makes effective the herringbone pattern of brickwork. The construction of the dome was completed without any scaffolding, thanks to these characteristics. The exceptional nature of Brunelleschi's work lies in the ability to control the construction process in its structural sense, and to produce an extremely innovative solution of a problem in which neither mathematical instruments nor physical models could guarantee the exactness. It is not possible to fully understand the work of Filippo Brunelleschi even from the point of view of the art history, neglecting his expertise in the static of structures, proved by his determination in making decisions about facts in which small errors could produce huge catastrophic consequences. After the Congress of 1977, Salvatore Di Pasquale and his collaborators continued to take lectures addressed to students of all ages and to common people to explain the sense of Brunelleschi's work. In the 80s, Aldo Regoli, a staff member of the laboratory of the Department of Costruzioni, realized a wood model of a circular dome with the supervision of and in collaboration with Salvatore Di Pasquale to represent the features of the herringbone technique and to help the comprehension of its mechanical implications. After 30 years, we decided to construct a new model, similar to the old one, which could merge the capability to clearly convey the structural content with the light weight of plastics used in 3D printing. After 30 years, we decided to construct a new model similar to the old one, which could merge the capability to clearly convey the structural content with the light weight of plastics used in 3D printing. As the previous wooden model, the digital model was obtained starting from the ideal proportions related to the edges of the real octagonal Florentine dome, drawing two concentric circular arcs pointed in 1/5 of the internal diameter and 1/4 of the external one, and subtending at the center an angle of 60 degrees. The region comprised between the internal and external arcs and the two radial line segments that connect their endpoints was then extruded rotating 360 degrees around the vertical axis of the pointed arch to define the volume of the circular dome. This has the same proportions of the dome of Santa Maria del Fiore, but has a circular base. The model was then cut into 11 rings, according to the cones on which the mortar bed joints of the real structure lay, and then into 204 voussoirs in all. 21 different elements were then isolated and intended for the 3D printing in polyamide. The printing technique used is the selective laser sintering, that is a powder-based 3D printing technology. The final dimension for printing was decided as a compromise between the necessity of transporting the model and assembling it, and was 45 centimeters in diameter, about half of the old wooden model. The voussoirs were given a hollow shape to reduce the printing time and the possible consequences of shrinkage, and to provide for possible filling with heavy material. The small scale employed and the low mass density of polyamide, in fact, produced very lightweight blocks. The whole dome is less than 1 kilogram, which mass can be in this way easily increased. Now we try to make some comparisons and some considerations about this experience. First of all, about quality. The wood model is faceted and quite heavy, not easy to transport, but very stable when mounted. The printed model is more geometrically faithful and is very light and easy to transport. As a con, we must admit that it is quite fragile, and the lightweight makes it less stable when mounted. About the process. The wood model is the work of a particularly skilled artisan who spent time in the design process and, most of all, in the production of a single piece. The production of a second model should have absorbed the double of the production time. The production process of the printed model can be addressed as a digital craftsmanship, as one single person or a small staff is able to control the whole process from design to production. The production of a small number of replicas would increase only the printing time and is competitive also with reference to the industrial process. Moreover, the graphical model necessary for the production can be transferred via web and, due to the wide diffusion of Fab Lab, permits a 0 kilometer production also in geographical areas usually thought of as marginal and isolated. On the weighing plate of cost of the 3D model, we have to consider about 24 hours of work of an expert designer and about 24 hours for printing and curing of the pieces. On the weighing plate of the benefits, we have to consider a lifetime of approximately 10 years and a fruition rate that can be calculated taking as a reference the about 500 students that had the opportunity to observe the model in its first 2 years of life. In this balance, the knowledge necessary to imagine this object, as well as the effective knowledge produced on people that attend the lectures, is not evaluable. At the same way, the value of a monument is still invaluable. Authors wish to thank Mr. Aldo Regoli for the suggestions and opinions useful for the realization of the model. The cost of the 3D printing has been covered with didactical funding of the Department of Civil and Environmental Engineering of the University of Florence. The 3D printing was executed by Constructor in Florence.